Hi everyone and good morning. Thank you for joining our webinar today titled A Small Spark, a Big Risk, ESD, ATEX and Antistatic Explained. I am Monica Romero, APAC Category Senior Manager, Single-Use Gloves at Ansell, and I will be your moderator today. Today we have Theo APAC Category Senior Manager, Mechanical Gloves at Ansell, as your speaker, who will discuss in depth on the ATEX and ESD topics of today's webinar. Before we start, let's go over a couple of practical tips that will give you a good webinar experience. Firstly, please note that your video and audio have been automatically turned off. If you are facing sound issues, you can log out from the webinar, restart your computer and rejoin. Ensure that your audio is on computer audio. After the presentation, we will have Q&A. If you have any questions, you can put it in our question box, or you can keep it for later on when we have the Q&A session. I have few tips and tricks to enjoy the webinar. Please bear with me, the list is a little bit long, but it will ensure that you have a good webinar experience. If you look to the top of your screen, you will see a row of actions which allow you to change the appearance at your interface. You may hover to perform actions, and you can click on the widgets on the screen to resize them. Let's go through the action items from the left to the right. First item is video, when you will see the speakers as. Second item is slides, where you will see the PowerPoint of the webinar. Third item is ask a question. If you have a question during the webinar, you can enter the question here. Once you have submitted your question, don't worry, we will have received it on the inbox and become empty again. So you do not need to resubmit your question. Fourth item is contact me. If you would like to be contacted after the webinar, you can click on the contact me button. Fifth item is the speaker's bio. Sixth item is request a sample if you would like to request a sample. You can click on other tools and you can select webinar survey. We will appreciate your feedback, as it will help us to make sure future webinars even better. Your resources with links on further information related to this webinar. We also have the reactions tool for you to engage with us during the webinar. Could you please react with an applause emoji to let me know you are there? Applause. Thank you. This webinar is supported with translation in. If you would like to use translation, please click on the widget as shown in the presentation. Click on the headset symbol for audio translations. Once you selected a language, the speaker in the video widget should be muted automatically. If this does not happen for you, please mute the speaker manually in the video. Click on the CC symbol if you would like subtitles. That concludes the practicalities. And on to something exciting. This is very exciting. We are bringing the lucky draw to this webinar as well. If you join in the first 5 minutes, you will automatically add it to our lucky draw. We will spin the wheel of names live on the screen and announce the winners on the spot. Today, lucky draw winners will receive Ansell's HyFlex 11819 personalized with your name. We will spin the wheel 2 times during the webinar. Please have a look out. If you are one today's winner, we will be in touch after the webinar to obtain your delivery address. Before we start this insightful seminar, I would like to remind you why Ansell and why we are different. We have an unrivaled portfolio, more than 1,400 styles in the industrial portfolio, including life science, mechanical, chemical, single-use, and body protection. We have deep knowledge. We have more than 700 quality, R&D, and regulatory experts. Regarding our sustainability journey, I would like to highlight our gold medal from EcoVadis, a trusted provider of business sustainability ratings. This gold rating places Ansell in the top 5% of more than 1,000 companies assessed by EcoVadis in the last 12 months. Effective partnerships and a global network of 14 manufacturing facilities and 21 distribution centers. With that, I would like to pass it over to Theo.
Thank you very much, Monica. Good morning, good afternoon to those from different areas around Asia. I would like to thank you for joining us, and I hope that you have a very insightful session today. I am Theo Oostveen. I have been for over 15 years working across safety in different markets throughout the world, as well as various industries throughout these markets of life science, manufacturing, food, mining, oil and gas, etc. All of these years, I have actually worked alongside with Ansell before joining Ansell in 2019, where I am now the product portfolio expert for a range that the Ansell portfolio has, looking after the Asia Pacific region. As Monica already mentioned, we'll be talking about ESD and ATEX today, and the content is broken down into the 7 areas shown, of which we'll run through. Monica has already been through the company presentation, but I'll define a bit further what is an explosion and how static electricity can cause explosions in the workplace. What are the different ATEX zones and how we define them? The European directive around ATEX and how to differentiate them, as well as how to know the difference between electrostatic discharge versus anti-static gloves and the standards that we use to identify those, followed by lastly, the ESD glove portfolio from Ansell. So, what is an explosion? To help us understand what we mean when we say explosion, I'll actually first run through something different, and that is, what is a fire? We have here a triangle, which some of you may have already heard previously or experienced in training or in your roles, the triangle of fire. And I'll run through each of the points and what we mean when we talk about the triangle of fire. The first point of the triangle we have is combustible products or combustible materials, which we often call fuel, something that needs to burn to create our fire. And in this case, the fire that we're creating is for a barbecue that you can see in the image there. The second element that we have is oxygen, which is readily available in the air around us at around 21% saturation. The third element of the triangle is our source of ignition, which you can see here is coming from a match. And together, we put these elements and we get our fire, and hence the triangle of fire. But let us look back at an explosion, and we'll remove the triangle this time. And we'll come back to this once we've been through a few more elements that we need for an explosion. This time, we'll add suspended products, which still act as a fuse or a fuel or our combustible material, but this time they're more spaced apart. And what I mean by this is, instead of the fuel being a solid mass, like the wood, we're now looking at gases and aerosols and dust that are suspended in the air, hence suspended products. But I'll talk more about this later on. The next element is confinement. And we need this condition of confinement where the combustible materials and oxygen are within an area, which then leads us to the last element, which we call explosive range. When we then link all of these elements and conditions together, we now form an environment where there is a risk of an explosion. And we call this the hexagon of explosion instead of triangle of fire. But first, let's focus on one element a bit further, the suspended products. So when we're looking at the suspended products and in different industries, there are these different forms of suspended products depending on the task being performed. So it's important to carry out a risk assessment to understand these different materials within your environment. Firstly, let's look at gases. These are elements that exist in a gas state under normal conditions, room temperature and pressure. Examples in different industries of gases would be acetylene used for welding, or propane for heating and cooking, methane also being used as a heat source, etc. Next, we have vapors, sometimes also referred to as aerosols, which are tiny, usually liquid, but can also be solid particles in the air. These come from elements that are usually a liquid state at room temperature. Take, for instance, ethanol or methanol. These elements being a liquid at room temperature, but they release vapors that go into the air, and that exposes them to the atmosphere and causes ethanol vapors and methanol vapors to be present in the environment, and they become our combustible products. Then we have dusts. Dust consists of small solids that are typically too large to be defined as the previous aerosols or vapors. It can be made up of various materials like soil, sand, minerals, and organic matter. But one of the largest problems in terms of these risks with dusts in the industry is in the food industry, such as bakeries and processing plants, where we have flour dust that becomes suspended in the air, and it leads to this explosive conditions in the environment. Another important element that we need to look at is the explosive range of these materials. The explosive range refers to the concentration of these suspended products within the environment, this confined space that we were talking about. And this can vary from 0% all the way up to 100% saturation in the environment. For different environments and materials, there are percentages of concentrations that have a risk of explosion. The minimum percentage of concentration for a material to reach an explosive state or condition is called the lower explosion limit, or LEL. The maximum percentage of concentration is called the upper explosion limit, or UEL. If a material exists between the lower and the upper percentage, this area is the danger zone where an explosion can potentially occur if it were to come across an ignition source, as we spoke about earlier. Outside of this area, you have a lower percentage where the amount of suspended solid is not enough to cause an explosion. So basically, we don't have enough fuel yet within this environment to be susceptible to an explosion occurring. Then there is also the area above the upper explosion limit, where the concentration of suspended products is actually too high, or you can think of it as if the amount of oxygen then, remembering we need suspended product, oxygen, and then our ignition source, and here we have too little oxygen to allow combustion to occur, like smothering a fire, for instance, by throwing a blanket over it and starving it of oxygen. In these areas below and above the limits, the danger of explosion are very heavily reduced or even no longer present. Here is some data so you can sort of compare different suspended products and their lower explosive limit and upper explosive limit within an environment. You can see, for example, if we take methane, the percentage of suspended product that creates the explosive environment is between 5% and 17% concentration within the air. Then, if you look at the other four products in the table, none of them have the same lower or upper explosion limits. And of course, even these limits can change depending on the environment, the temperature, or within tanks, for instance, where the pressure of these chemicals might be different. But before we move on, let's go to our first question of the day. You should be able to see on your screen now a question. You should be able to answer the poll by clicking on the response that you need. So question is, in your opinion, which product poses the greatest risk considering the below explosive range? We'll give you some time to click on your answers. We might give everyone about another 10 seconds. All right, let's see how we went. All right, very good job. So indeed, 72% of you answered acetylene, which is absolutely correct. And the reason why this poses the greatest risk is because that explosive range is so large. So the lower limit being 1.5% and the upper being 82%, it means that even a little bit of acetylene in this environment, or all the way up until 82% saturation, you have this risky area where an explosion could occur. So indeed, all those who answered acetylene, well done. All right, so we're now on to the first part of our exciting lucky draw to be drawn out and find our winner. As Monica mentioned earlier, you will be receiving a custom prize for yourself. So if you joined in the first 5 minutes, congratulations, you are in the running to win. And we will just let that go now and see who our winner is. Here it spins. Who is it? All right, there you go. So congratulations to our first winner. We will be in contact with you at the end of the webinar and ensure we get your details so you can get your prize. Congratulations. Okay, so back to our explosion and hexagon of explosion. We've spoken about the new elements, but we haven't yet spoken about confinement. So when we spoke about explosive range, we looked at the percentage of concentration of suspended product in the air. In doing so, we measured the risk of explosion in a small sample of an environment, for instance. So without this small sample or without this confined environment, we also wouldn't be able to measure the right parameters for the explosion to occur. So how much oxygen and how much suspended product there is in order for ignition and in order for explosion. And that area, that defines our confinement. And the area of which this explosion range exists becomes important later when we talk about the atmospheric explosive zone or ATEX zones. So let's continue with our hexagon and concentrate now on the source of ignition. And in relation to an explosion this time, not in terms of a match and a fire. So amongst literature and amongst the standards, there are 13 defined definitions for a source of ignition, which if you look, and for those of you who have a keen eye on the slide, will see there's actually only 12 images and thus 12 examples listed here. But I'll touch on that because electromagnetic waves, we include both the short and the long waves together. So that's actually two sources of ignition, but for this image, we've only got it listed there as the one. Of course, when you're looking at these images, some of these are more obvious and easily understood, such as a hot surface, the open flame, or the sparks, as to why they could be seen as a source of ignition in areas such as welding or working with metals and grinding, for instance. But there are other less obvious examples within our workplace, such as electrical switchboards or even faulty cables, where you can have electrical currents and sparks occurring, trying to discharge through the air instead of through their electrical designated components of cabling or switches and that type of thing. And that could cause a risk of ignition. Static electricity, of course, the topic of today. We'll come back to that and discuss that further, and we'll define what that is. Lightning, of course, as you can imagine, that causes fires within nature when that comes into contact with combustible materials, no different like what we've spoken about in our triangle and hexagon. You get the oxygen, you get, for instance, a tree, and you can start forest fires and that type of thing through exposure to lightning. The electromagnetic waves, not something that is visible, but you may have seen in movies where they make a call to a mobile or cell phone, and that is the cause of an explosion, trying to sort of indicate that the long or short electromagnetic waves to this phone has been the source of ignition. Ionizing radiation, this refers to the energy that breaks an electron away from an atom, so really down to a molecular level. Without getting too technical on this, it's basically the energy that causes a chemical composition of a material to change. And when you get this in an exothermic reaction, or a reaction which produces energy, this energy can be extremely high. And this is where we see, nuclear and radioactive materials atomizing and causing those big explosions that we know of, right? Due to that large energy. Ultrasound, so this is the moving of sound waves in a controlled way. When these sound waves are concentrated and at high frequency, you can actually cause a material to heat up quite significantly. That can cause your ignition source. Adiabatic compression is an interesting one, which is when a gas is compressed within a confined area. A good example of this is, for instance, the cylinder of a combustion engine in a car. A diesel engine, for instance, does not contain any spark plug to create that explosion in the cylinder of a car. It purely relies on the pressure of the cylinders, of the piston pushing on the cylinder, and when you get that perfect ratio of diesel to air at the compression, it causes an explosion. So that is a direct result of that adiabatic compression. Chemical reactions, of course, you get the right chemicals and you mix them together. It's a bit self-explanatory. That often occurs, happens to create heat and even, of course, flames and that type of thing. So that summarizes the 13 different types of ignition sources. So it's really important that in your risk assessment, you have a look and you could probably identify as well as manage any of those ignition sources to ensure a safe environment. So let's move on to static electricity, which I mentioned as one of the source of ignitions. So here we have an object, and objects can exist in different states of electrical charge. When an object contains, like this one you can see here, the same number of positive and negative charges, we call it neutral. And so we have a neutral object. We can then also have objects that are negatively charged, meaning that the object has more or an excess of negatively charged particles. And we can use this negative symbol up the top there to show that this object is negatively charged. We then, of course, can have the opposite, where we have positively charged objects, meaning that we have a deficit of negatively charged particles or an excess of positively charged particles within the object. And thus we can use this positive symbol to show that. When we have a negative or positively charged object, we have objects that we say are in an electrical imbalance, meaning that there is more of one than we have of the other. And like many things observed in nature, these objects want to find a balance. They want to find a way to pass those charges to each other or to get rid of the excess positive or negative charge some way in order to equal out. All right. When this happens and when these charges come out, this is when we get a discharge. And you might hear us say electrostatic discharging, and that is what we're talking about. These charges leaving an object. So let's have a look at this example where we have two objects, one with a positive charge of static electricity and the other one with a negative charge of static electricity. All of this energy has the potential to release into another object. And so we call this potential energy. We now take these two objects with their imbalances and they come close together, enough that the charged particles can jump from one object to the other object as they're trying to find this level of balance. When these charges leave the object, as I mentioned before, you get the discharge, the electrostatic discharge, or ESD, meaning that the electrical charges that were once static with that potential energy living in an object are now leaving and releasing that energy. All right? The danger of when this is released is if it's released uncontrolled, and this electrostatic discharge then occurs as a spark. And as we've spoken about in the previous slides, this spark can be a cause for the ignition. That is your source for ignition. And in the environment of the hexagon, you then have explosions that can occur. All right, so electrostatic discharge can sometimes happen undetected. You can't feel it, you can't see it, but it can also happen where you can feel it and you can see it. And I think many of you would have experienced this in your life, but let me just give you a very common example of when this may have happened and see if you can relate. All right, so think back if you've found yourself stepping out of a car or after having walked along wearing particular clothing, especially those that have polyester and some plastics through it and that type of thing, and then you've touched something, especially something that's metallic, and you have felt a zap from the end of your finger. All right? Anyone who has experienced this, felt this, heard it happen to someone else, they have experienced an electrical static discharge, an ESD event. Now, it was a small amount of static electricity and it didn't cause any issues, but that is an ESD, all right? And if we take your body in this instance, take the body as the object that was being charged up and causing the imbalance, that's the buildup of static electricity, which had this potential. And once you touched a surface, that energy left your body in an event to try and earth or ground itself, meaning that it formed a pathway to the natural earth that we all live on, literally the ground, and that static energy left your body as a spark in order to do so, to restore the electrical balance that we're talking about. So this spark is the electrostatic discharge, and it can easily occur, and it happens multiple times every day around the world. All right. And so to ensure that during your risk assessment, you're aware of this, you also need to look at the materials and equipment and things like that within your workplace to make sure that the workers are safe from becoming electrostatically charged and this potentially happening. So let me now give you an industry example and run through how this might work in terms of a workplace environment. So say you have here a tank, and then in this tank, we are putting different chemical products that we are using to make a mixture, and we're agitating that together. And this has left the tank with a positive charge. In the meantime, we also have a worker who is coming from another area, and due to walking around, touching other surfaces and maybe absorbing electrical charge in that process, whatever it might be, this worker has a negative charge. And you can imagine what would happen if these two objects, the person and the tank, came into contact with each other. Now, in order to avoid the transfer of these charges between the two objects of the tank and the person, a lot of processes have written in them what we call earthing, an earthing method. So as I previously mentioned with the car example, where you're charged up and then these electrical charges are trying to get to natural earth, here you can see this method of earthing allows the charges or allows the objects to be connected already and linked to the natural earth, all right? Trying to get these imbalance of positive on the tank and negative charges on the person to leave those objects and balance themselves out instead of having to do it via each other. So that is the method of earthing or grounding, and that is what you're trying to achieve by doing that. All right. So we know that when we're working with chemicals in the tank, that we want to wear PPE in order to protect the worker and to wear the gloves. But here we've got the worker now with a glove on. But let's imagine that the glove they're wearing isn't providing the right protection. And what I mean by this isn't the chemical protection only, but the electrical protection as well. So I'm talking about gloves that are able to hold or accumulate this negative charge. All right, which you can see here. And as you can see, the glove surface is holding onto a negative charge, and they are not able to reach ground or to transfer safely away these charges to a surface because the glove doesn't allow charged particles to run through it. Okay? Now, I am getting a little bit technical here, so if anyone has any questions, please feel free to put it in the question and answers area, and we'll address them at the end when I finish the presentation and answer them for you. So let's say the worker then comes into close proximity with the tank. These negative charges, unable to go through the earth of the person, will then have to discharge via the tank, potentially causing that source of ignition to occur, all right, in order to try and balance out. And it will actually use the tank's earth to travel and try and balance, all right? Now you then add our explosive range, which we spoke about as part of our hexagon of explosion, which you can see here is represented by a cloud, say vapors from the chemicals that would be mixing and agitating in the tank. That is where you have that risk of the uncontrolled spark occurring, ESD happening, and that leads to your explosion. Now, let's take this same example, but we'll change one thing. We will change that glove to now be an ESD certified glove. Now, due to the properties of the ESD glove, these charges are now able to travel through the glove, unlike before, and go through the object, which is now earthed and properly linked, and thus removes that charge away. And this is the importance of following the practice of not just having your earthing, which is a common process that is done in a lot of these ATEX areas, but also the right PPE that is ESD certified. Earthing is very important and should be a part of the process, but it is, I have to mention, it is important to also have both of them in there, earthing and ESD. If you have ESD, but you don't have the earthing link through the person, it still doesn't allow those charges to travel through the person and get to the earth, right? Because you haven't earthed them. It will still try and earth through an object. So it is important to have both to create this safe scenario. Okay, as I mentioned, any questions, please put them in the Q&A section, and we'll move on to ATEX zones. So now that we've covered static electricity, ESD, electrostatic discharge, let's look at these defined areas, these confined areas that we spoke about as part of the hexagon of explosion. The term ATEX itself, I've mentioned it a few times, is actually from the words atmospheric explosive. And we take the first two letters, AT, and the second two letters of explosive, the EX, and we get ATEX. And as the words described, this represents an atmosphere that has all the elements we need in it of chemicals, gas, vapors, dust, in order to create an explosive environment. So here we have an example of a tank in a room that is then in a workplace. And let's imagine that we have two possible contents that could be in the tank, being either a gas or a dust. So according to the directive, there are 3 zones that we define within our ATEX classifications. If the content here within the tank contains a gas or a vapor, we refer to that as zone 0. And in general, zone 0 has no workers. It is a confined space in a tank. We are not going to have people working in there. Really, the only time you have these confined areas with workers in them is when we have emptied the tanks and we might get in there to clean them out. And there is special PPE and things that we use for confined areas as well on top of that. But generally, zone 0 areas, no workers. If the tank, though, contains dust instead of gas, we define this area as 2020. It's the same zone and everything. The definition is just to identify the difference between that zone having a gas in it or that zone having a dust. So then we have zone 1. Now, this zone could be 1 metre, 2 metres or larger, depending on the risk assessment to be completed within that workplace. Again, zone 1 for a gas, 21 if we have a dust. So gas vapors 1, 21 for a dust. But it's important to know here, this is the area around that confined zone 0. And depending on the different conditions, that area can be larger or smaller. So it's important to address that within your risk assessment. Then we have zone 2, which is the rest of the room in which this tank of zone 0 and the explosive area around that of zone 1 occurs. And then same thing again, based on gas or dust, we have zone 2 or 22. Now, the difference between these zones basically is zone 0, 1 and 2 have different increasing probabilities of explosion occurring, given 0 having the highest risk or probability of an explosion occurring, and then zone 2 having the lowest probability. And so part of your risk assessment will show you which areas would be defined as a 0, 1 or 2, or a 20, 21 and 22. So here we have an image or an example of a live working environment where these zones occur. So you can, if you have a look inside, you'd be able to see within the tank, you've got your zone 0. There's an operator who's opened the tank. This commonly occurs if they were, say, adding more chemicals into the mixture, perhaps taking a sample of what's in the tank in order to do further testing. And so you can see quite easily, you then create that area of zone 1, where the zone 0 has expanded now outside of the tank into an area where the operator is for the potential explosion to occur. And then obviously as that then spans out, there might be ventilation and air movement in the room, and the rest of the room would become your zone 2. All right, so we heavily advise get your ATEX zones rated properly in your workplace so you can clearly understand if something like this was to occur within your workplace, where your different zones of 0, 1, 2 was 20, 21 and 22. So now I'd like to share an example of how quickly something like an explosion can occur in an area. And you'll see here a chemical tank, a worker or operator comes along, looks like they're just maybe wiping up an excess, a spill, and an electrostatic discharge occurs. And you'll see what happens in this video very quickly. Okay, so I let it play there a couple of times so that everyone could see just how quickly and just how easily it can occur. And, you know, potentially when you're looking at that situation, you're seeing chemicals, you're seeing tanks, everything looks like it's stored properly. A worker comes along, goes, oh, there's a spill, I'm just going to wipe that up. And then bang, there it went. And I don't know if everyone saw it, but the tank, that international bulk container, the white tank that you saw, completely expanded. The only thing holding that still together was the steel frame around it. You know, the worker was running off to the side. It very quickly and easily can happen. And you can imagine if you were that person there, the amount of trauma you would have gone through in that event. So here we have another example of electrostatic discharge outside of a workplace now, but also just how easily you can recreate something like this. Definitely advised, do not do this at home, but just an example here. Okay, so I have to be clear here. Please do not try this at home. And you can imagine how in a different environment where they've recreated this hexagon of explosion, how things can definitely escalate and occur. But what you saw there is they created that static charge, that potential energy by what looked like pulling a plastic acrylic-based blanket over the top of the woman there. Then that static charge they used to light essentially a gas stove by creating that suspended product by turning on the stove, and there was that confined area immediately around the burner. When she went to touch the metal burner, which is then connected to the building, which touches the earth, so there's your link to earth, you saw the spark, the electrostatic discharge, and then that caused the gas to light. All right. So let's talk a little bit now about the European directive around ATEX. So how they sort of manage and make sure the safety, and there's a couple of different approaches to it here. The two directives are, one, the economic directive, and then there is the social directive there. All right. So the economic directive is dedicated to manufacturers, so those making equipment and those making things that go into ATEX zones, and it is defined to make sure that they're adequate for use within ATEX zones, these pieces of equipment. Then there's the social directive, which looks at workers being protected in these regions, okay? So as I mentioned before, the economic directive, all right? So this is for manufacturers, and it basically says that anything electrical or mechanical piece of equipment is properly designed so that it will prevent these ATEX environments from being created by not releasing any gases and that type of thing into the environment, but also preventing any source of ignition from occurring. So you can see there that it is covering the areas of the hexagon of explosion that we spoke about. So it's removing that risk of explosion from occurring. What's important to know here is that PPE is not within the scope of this directive. All right, PPE falls under a different regulation. And I need to clearly define this because the term ATEX glove, there isn't actually anything within the ATEX directive around PPE and thus around gloves and the way that they need to be manufactured with the ATEX directive. So let's look at the other side then, shall we? The social directive around protecting the user. Is there something in there for gloves? So this directive says that in an ATEX zone, the users need to wear the necessary PPE and that the gloves cannot be a source of ignition or a potential static charge, all right? So it's to say that basically is saying the user is responsible for ensuring that they are wearing the correct PPE when they are within these ATEX zones. But again, it doesn't say anything around what the correct PPE is, okay? So really what we're saying here is there isn't an ATEX glove. That terminology is incorrect, but I'll touch on that because we'll be thinking, all right, I'll first touch on how do we define ESD and antistatic and how this relates to getting, okay, we have a glove that we can use in an ATEX zone. Okay. So firstly, when we look at the EN 1149, so the standard around electrostatic testing, this testing was made and designed for clothing, for materials in clothing, not for gloves, okay? And when you look at the particular EN 1149-5 criteria, it outlines that the below 3 criteria of half decay time being less than 4 seconds, a shielding factor of more than 0.2, or a surface resistance of less than 2.5 times 10 to the power of 9 there, is satisfied. So it just needs to satisfy any one of these three criteria in order to achieve the EN 1149-5, okay? Then you can use this pictogram that you see here, and you can display EN 1149 underneath that electrical lightning sort of spark bolt looking pictogram, all right? However, as I mentioned earlier, this was intended for suits, okay, not for gloves. And so you cannot use this when it comes to your gloves. So you're going, okay, what can I use then? You're telling me what I can't? Let me show you. So when it comes to gloves, what can we use for ATEX zones? This is where we have vertical resistance, which is different to the test being done for the surface resistance that I showed in the EN 1149 earlier, okay? Now, when you're looking at this, and if you have a look at the EN 1149, there isn't actually a requirement for any vertical resistance. So the EN 1149 is not what you would look at in order to see whether you have an ATEX rated or an ESD certified glove to be used in those environments. And something that's important to know is there is within the EN 1149 a testing method for vertical resistance, but there isn't actually outlined within the testing a limit. So it's not saying you need to be less than a certain amount of ohms in order to pass or to get anything. It's basically just defining the test method that you can use to test vertical resistance. So it's just giving you a number, but it's not actually telling you, okay, based on this number, it means something, okay? So we're basically saying here, EN 1149 cannot be used. There is, however, in the EN 16350, a defined requirement for gloves and the testing of the vertical resistance for ATEX zones, all right? So whereas in the 1149 or the 1149, it doesn't have the appropriate limit, the 16350 does have it. And it is saying that for each of the materials being used in the glove, it needs to have a low resistance, a certain resistance. And this amount is less than 1 × 10 to the power of 8 ohms. Now I keep saying ohms, that little symbol that you see there, some of you may have already seen it, know what it is. That is the standard unit of measurement for electrical resistance. You can do that for cables, for components, whatever it might be. So we're using the same method because we are measuring the discharge of an electrical current through our gloves and through our materials, okay? If you meet this requirement of less than 1 × 10 to the power of 8 ohms, you can then use the same pictogram, but this time it says EN 16350 underneath. And we can use this for gloves. So let me give you an example of how these two sort of can work together and give you different values, but how that works and what that means for the actual gloves and materials themselves, okay? In order to pass, and we can define an anti-static glove, okay? You could go and do the testing, and if you get a result between 1 × 10 to the power of 4 and 1 × 10 to the power of 12, you can then define that material and define that product as anti-static. So it will not cause a buildup of charges within the product itself. Okay, so that static energy that we spoke about and that wants to leave, this material, if it falls within this range, can be defined as anti-static. Then within the EN 16350, this is the point. If you are less than 1 × 10 to the power of 8, you can then also claim that you are electrostatic discharge certified. So you can use that product, that material then in the ATEX zones, okay? As you can see, this is between the points of 10 to the power of 4 and 10 to the power of 12. So an ESD glove can be ESD certified and anti-static, but then there's this area above 10 to the power of 8, where in fact you can have an anti-static glove, but it is not ESD certified. So it's very important to know what the actual values are. And I'll give you a real live example of that in a glove that we have over here. So take this glove here, and looking at the two slides that I've showed you, the EN1149 and the EN16350. On the EN1149, it needs to pass one of those three tests we spoke about. And here it has a half-time decay of 0.01 seconds, which is clearly less than the required 4 seconds. Okay, so it gets a tick for antistatic based on that one parameter. Okay, but then when you do the EN16350, its result is almost 2 times 10 to the power of 10, well above the 1 times 10 to the power of 8. And you might say, oh, well above. Well, it's only a factor of 2. We were 10 to the power of 10. We only need to be 10 to the power of 8. There's only a difference of 2 there. But let me show you how it doesn't quite work like that and what we mean here. So 10 to the power of 8 and 10 to the power of 2, only a difference in a power of 2. And it's just a little bit of maths here. But 1.24, we're in the Asia Pacific region. I've chosen Japan here. The population of Japan, when I looked up, is around about 124 million people. Okay, so 1.24 times 10 to the power of 8. Now, what's 10 to the power of 10 then, if it's only a factor of 2? Actually, the population of the entire world is almost 10 billion people, which is 1 times 10 to the power of 10. So when you're looking in terms of the difference between and trying to compare the resistance here, massive difference, very large difference, even though it's only an 8 to a 10, that factor of 2 is a very large amount. So how can I check? How can I make sure that the gloves I'm getting are certified to the right standards? So at Ansell, you can go to our website, find the web page of the glove you have in question, and we will have a section on the website for documents that you can download. And here you'll find a different list of documents for that glove, one of which is called a Declaration of Conformity. And on that Declaration of Conformity, you will see, as shown here in the slide, the pictogram for EN16350. If you then need more information, you can contact our team, go to your Ansell representative, and we can provide you even the results that define that we have clearly passed the requirements for the EN16350. I'm sure we'll be more than happy to help you. So that clarifies all of that, the ESD rated versus anti-static, different ATEX zones, and everything like that. So what have we got in our portfolio that can help you? What can help you keep your workers safe, keep your environment safe? But before we do that, I'm going to let you guess. You tell me, how many gloves do you think within our portfolio we have that comply with the EN16350? I'll give you about 30 seconds to answer, and then we'll go and see what everyone thinks. I'll do another 5 seconds and then see where we were. All right. Well, a lot of people went for more than 10. Look, unfortunately, it's not quite there. We're definitely working on it, and it will be more than 10 very soon, I'm sure. But those who answered 7 to 10, you are correct. So here on this slide, this is our current portfolio. As I was saying, there will be more coming. That complies with the EN16350. So we have a range here, 4 of which come from our mechanical portfolio, and the differences between them being the cut rating there. So we've got some multi-purpose ones through to some medium and high level cut range. We also have the Microflex 94242 from our single-use portfolio, and then we have another 4 gloves from our chemical portfolio there as well. So a good range so far across all 3 of our major portfolios in chemical, single-use and mechanical, and more to come. So watch this space. If you want, you can scan the QR codes there. They will take you to the product pages on the website, where of course you'll find those declarations of conformity conformity, or if you have any other questions, please feel free to reach out to the Ansell team members. Hit the button for us to contact you afterwards, and we'll get in contact with you and help you with whatever you need. All right, on to our second lucky draw and our lucky winner. So we'll spin the wheel again and see who our lucky winner is this time. Here we go. There you go. Congratulations to our second winner. So both our winners, we will reach out to you after the webinar and make sure that we can get your details to arrange for you to receive your prize. All right, so onto the Q&A section. I'll just scroll down and have a little bit of a look. If you've got any questions, please pop them in. I know we're very short on time. There's only 3 minutes left, but I'll try and get onto them. There's one here, the difference between vertical resistance and surface resistance testing. So the surface resistant testing, if you can imagine, you get a material and lay it down on a table, let's say, and you've got 2 probes on either side of that material, and we are actually testing how much resistance there is for an electrical current to pass through from one probe to the other, right, across that material, let's say. When we then go to vertical resistance, or sometimes called volume resistance, now imagine you have a probe on either side of the material and you are measuring the resistance that it takes for that electrical current to travel through the material now. So not over the top of the material or across the material, but now to pass through that material. That's the difference between the surface resistance testing and vertical resistance testing. Let's see what else we have here. Which would be the best recommended product from our 9 in the range? This is a very difficult one. And I might take this one last because I know we're very short on time here, and apologies for any of the other questions in there. We'll contact you afterwards and definitely get you the answers that you seek. It is very hard to say, here is one glove that is going to do everything that you need it to do. It is very dependent upon your workplace, your different applications. Do you need, obviously, chemical protection as well as cut protection, or do you not have either of those risks and you just need something for abrasion as well as ESD? So it's very important in all of this when we're looking at the hexagon and we're having a look at the different elements that create an explosion. In your risk assessment, look at the suspended solids that you have. Most workplaces have multiple chemicals. Understand what your chemicals are, even what concentration and saturations you're using them at. One company might be using 70% ethanol in their cleaning, another one, 100% concentration, and how that differs in terms of the vapors going into the environment, then the different types of, sources of ignition. So you really have to look at that from almost a customized basis so that you're making sure the solution that's being put forward is a customized solution for your workers in your workplace, because there are no 2 workplaces that are exactly the same, even if they're in the same city but in slightly different locations. One of them might be closer to water where it gets more wind and breezes off that sort of area, and it all changes, right? So it's really important that you are doing your risk assessments to the fullest and ensuring that you're getting your customized response from that. So sorry, that is all the time we have, but I will make sure we get to the other questions that are in there, and I'll pass back over to Monica, and I hope it was an insightful session for everyone, and I thank you for your time.
Thank you, Theo. This ends our webinar today. Thank you everybody for your participation. We hope you learned something new and we are able to answer your questions. Help us improve for our future sessions by completing our webinar survey. Have a good rest of the day and see you next time.